useful things written to a high standard of code that are all posted for free at this thing called CRAN, which stands for the Comprehensive R Archive Network. And there's a search capability, so you can go to CRAN and type in what you're searching for, and you'll find all the functions that are, if any, that are available there that will help you with that. And then if instead you type WinBugs, all lowercase is just as good as anything else, you get to the Bugs project, WinBugs, and you will see that they have various things, including downloads and discussions of extensions, GeoBugs for geospatial statistical modeling with WinBugs. The part called running from other software, let's have a look. So the R to OpenBugs package allows OpenBugs to be called from R. That's pretty cool. So if you go to the OpenBugs people and install OpenBugs on your platform, it looks like you can run it from inside R. So that's something you could try. Anyway, you guys can read through this and see if you can kludge together something to work for so that WinBugs works on your Mac. What's that? That is another possibility. I'm not going to be demonstrating it in here. I'll be showing WinBugs. But JAGS is another set of routines. Was JAGS written in R, or what environment was it written in? Do you recall? Uh-huh. I believe that JAGS is not able to fit as broad a variety of models as WinBugs is. And so I'm going to show you examples in WinBugs in this class, and then I'll try to do my best to help you bridge from the Windows environment into your environment. That's going to be how we're going to try to do it. Okay. There's a diagram that's part of the handwritten notes that I wanted to share with you here that helps to explain the difference between probability on the one hand and statistics on the other hand. Lots of people in the Valley are doing A/B testing, in which you create two different versions of essentially the same thing, two different versions of the Google search experience, or two different versions of the eBay shopping experience, and users get potentially randomized into one of those treatments, you could call it, and then you gather data on them and look and see which one seems to be doing better than the other on whatever outcome you're monitoring. When you're done, you have a data set. You'll have a treatment data set and a control data set, for example. And those are over there in the part of this diagram called the sample. That's your data. And it's interesting to find out how things went in your sample, as I was saying this morning. But it's even more interesting to try to reason outward from your sample to the broader universe of what would happen if you implemented that particular new version of the web experience or whatever it is in the future. And then the future users under that new web experience become the thing you're trying to generalize to, which in statistical language would be called the population. So the population is a bigger universe, and the sample is regarded as like a random sample from it. And sometimes it's even literally a random sample from it, but at other times the best you can argue is that your sample is like a random sample from that population you're interested in generalizing to. And the cool thing about the diagram is that the arrows can go in either direction. If you know the population, then you can use mathematics to work out, using probability, to work out the likely composition of the sample. And that, in this direction, is probability. Whereas if all you know is the sample, and you want to reason backwards to say something about the population that it is like a random sample from, that's the other direction in the diagram, and that's statistics. And it connects with ideas from philosophy and from logic as well. Sorry about the noise. I think that's going to work okay. People in logic talk about deductive and inductive reasoning. They also talk about reasoning from the whole to the part. Also reasoning from the cause to the effect. We talked about that this morning. And so all of these words are part of the diagram as well. The population can be regarded as like the whole, and the sample is like the part. And the population can be thought of as like the cause, and the sample is like the effect. And reasoning from the whole to the part in logic and philosophy, people refer to as deduction, deductive reasoning. And reasoning backwards from the part to the whole, that people refer to as inductive reasoning. And another name for that in statistics is inference. And so inference is equivalent to the phrase inductive reasoning. And if you look at the picture, you can ask yourself, just as Mr. Bayes did, is it easier to reason from the population to the sample, or from the sample to the population, or are they equally easy? What would you say? Easier to reason from the population to the sample? Got to be a lot easier, right? So probability is easier fundamentally than statistics is, and that's why we often start, that's why when you're learning this stuff, you take probability classes first, and then you take statistics classes second. So that's kind of a top-level diagram that shows some more about what we're doing in here. We're going to be talking about random variables pretty soon, so I think I'd like to do a short review of some stuff about random variables, just to make sure that we're all on the same page there. So let's talk about one random variable at a time first. Random variables have a formal definition in the Kolmogorov approach to statistics that has to do with sets and functions operating on sets, but we don't need to go there. Just think of a random variable as something that takes on values in an outcome space that you're interested in, and that behaves in a non-deterministic manner. That's a way to think about it. So people tend to use capital letters for random variables and lowercase letters to stand for the values that they take on. So capital Y might be a random variable. And when we're talking about random variables one at a time, by far the most frequently used random variables are the ones that take values on the real number line. So you could call such a thing a real valued random variable, and that would be abbreviated RV, otherwise known as RV squared. So that's what that phrase RV squared means. So it turns out that you can completely, if you're trying to tell someone, if you have a random variable you're thinking about, and you're trying to describe to someone else how that random variable behaves, you can tell them everything that they need to know by describing what people call its cumulative distribution function, or CDF for short. And here's the definition of it. People using in full notational glory, people use the notation capital F for the cumulative distribution function, subscript capital Y to tell you which random variable it's the CDF of, and capital F evaluated at the point little y, which is the value that the random variable can take on. And it simply keeps track for you the probability that the random variable will have a value that's no greater than that number, little y. So that's the fundamental unit of describing the behavior of a random variable. If you can tell someone all the probabilities to the left of a place, so to speak, on the number line, then you're in good shape. And so what do these CDFs look like? Well, since it sweeps probability to the left of a place, it can't ever go below 0. So here's 0 and here's 1. And it can't ever go above 1. And since it's always adding extra probability as you move to the right, it can never get smaller either. So it's monotonic, non-decreasing. It can't ever go back down again. So a typical picture of a continuous CDF might be something that looks like an elongated S, for example. That would be an example of a CDF of a continuous. CDF of a continuous real valued random variable. So, and those objects turn out to be the primitive object. If you tell someone the CDF of a random variable, you've told them everything they need to know about the random behavior of that thing. And nicely behaved random variables are either what's called discrete or continuous. And the words mean just exactly what you would hope that they mean. Discrete means that it takes on a set of values on the number line that have distinct gaps between the possible values. So when you're counting, if you try something over and over again, for example, I put a bullseye on the wall and I throw darts at it, and I count, I'm going to throw 10 times. I count how many times on the dartboard, how many times I hit the bullseye. The numbers could be anywhere as integers from 0, 1, 2, dot, 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 up to 10. That would be a discrete random variable because there's big gaps between the possible values. A continuous random variable instead has no conceptual gaps between the possible values. It just varies continuously along the number line. There is a distinction worth mentioning. Every time you try to measure something that is conceptually continuous, for instance, later on we're going to talk about the weight of a little block of metal, the measuring process always discretizes it because we're not capable of measuring anything with an infinite number of significant figures. So everything that we measure is actually, strictly speaking, going to come out discrete because there's teeny little gaps between the possible values that arise from not being able to get any more accuracy than that. But we're still going to call a quantity like that a continuous quantity because in principle, if you had more accuracy, you could have gotten more significant figures. So discrete random variables have the property that there are structural gaps between the possible values. With the bullseye, throwing the dart at the dartboard example, there's no way by measuring things any better I can end up with half of a bullseye half of the time. I either have to have 0 bullseyes or 1 or 2. Those are structural gaps between the possible values. I mentioned that nicely behaved random variables are either one or the other. There are lots of random variables that arise in work here in the valley that aren't either one or the other. They're a mixture, partly discrete and partly continuous. If you're measuring something that is often 0, for example, but when it's not 0, it has some continuous value bigger than 0, that would be a nasty sort of mixed random variable that has a point mass that's rather a discrete mass at 0 and then has continuous mass to the right of 0. But mostly we're going to talk about things that are either discrete or continuous and not talk about that kind of mixture random variable. So I just mentioned here the same thing we noted before. Distribution functions are always non-decreasing in the argument y, and they're always between the values they take on are always between 0 and 1. You can equivalently characterize a discrete random variable by its so-called probability mass function, in which you keep track of how much probability is associated with each of the discrete values that it takes on. So PMF for short, probability mass function. And the simplest possible discrete random variable is one that follows a so-called Bernoulli distribution, named after that same Jacob Bernoulli guy that I may have mentioned. Did I mention him earlier today? I forget. Anyway, the Bernoulli brothers were very good mathematicians, Swiss mathematicians, working in some of them in the early 1600s, and then the family continued well into the 1700s. And the Bernoulli random variable is our old familiar binary outcome. It's either yes or no, it's either 1 or 0, and the success probability for getting a 1, we could use any of a variety of symbols for, but I'm going to use the Greek letter theta right here. And so the probability mass function has the following property. The probability that the random variable capital Y takes on the value little y, which could either be 0 or 1. It's probability theta when little y is 1. It's probability 1 minus theta when it's 0. And probability 0 for all other possibilities along the number line. And so you could draw that by drawing a number line and then a vertical axis for the probability. And you could put a point mass of height theta at 1 and a point mass of height 1 minus theta at 0. Or equivalently, you could draw a little histogram in which the bars were 1 unit wide, and you could have a bar that was 1 unit wide and went up to a height of theta for the 1 and 1 minus theta for the 0. This little picture represents a Bernoulli distribution where theta is bigger than 1 minus theta, by which I mean theta is bigger than a half. And if you don't know what theta is, and you want to imagine letting theta vary amongst all its possible values, since it's a probability, it could be anywhere between 0 and 1, then you get what people call a family of probability distributions. So this is not just one probability distribution, it's a whole family of such distributions, and the jargon is indexed by the one-dimensional parameter theta. Okay, now, this is a computer science way of writing this random variable's probability mass function, because it's an if-then-else sort of story. The probability mass function equals this if y is this, or else it equals this if y is this, else it equals that. But there's actually a slick mathematical way to write it all in one expression, which you may or may not have seen before, namely this expression over here on the right. I can compress all that computer sciencey way of talking about it simply into the expression theta to the power y times 1 minus theta to the power 1 minus y. And you can check and see if it works. If little y is 1, you get theta to the 1 times 1 minus theta to the 0, and that's theta. And if little y is 0, you get theta to the 0 times 1 minus theta to the 1. So it works, right? So, and we're going to use that representation pretty soon in our next case study. What does its cumulative distribution function look like? Well, to the left of 0, there isn't any probability yet. So the CDF is 0 up to that point there. And then right at the point 0, it jumps up to the height of 1 minus theta, because we've accumulated that much probability so far. And then between 0 and 1, it stays constant, because there isn't any new probability to sweep in as we're going from left to right. And then as soon as it gets to 1, it adds theta to 1 minus theta and jumps all the way up to 1. So the CDF that goes along with that probability mass function looks like this. So there's the probability mass function, and there's the CDF. It's 0 out here, and right at that moment there, it jumps up to 1 minus theta. It stays that amount until right there, and then it jumps right up to 1. Now, what about if y is continuous? We could try the same trick and ask what's the probability that the random variable y, capital Y, takes on the value little y for a continuous random variable. But something funny happens. If you try to give that value, if you try to give that probability of value any value other than 0, you run into trouble right away, because there are uncountably infinitely many values for the random variable capital Y. And if you were to add them all up, they would add up to infinity. And we know that all the possibilities have to add up to 1. And so for any continuous random variable, the probability that that continuous random variable exactly takes on a specific point right on the number line has to be 0. Otherwise, if you try to add it up, you'd get too much. You'd end up adding up to infinity. So subtlety is needed. We have to be a little more subtle. And so here's what people do. For a continuous random variable, capital Y, with CDF capital F, if you can find a function lowercase f such that the integral of lowercase f from minus infinity up to y equals capital F at that point y, then little f is called the density function of that random variable. And basically what it does is it's a smooth curve that represents the local amount of probability that's near the point you're thinking about. And it won't look like that S sort of curve. It might go up and then down again, for example. But if you took the up and down aspect of the density and started accumulating probability from the left, you would get one of those S-shaped things. That's the CDF. And so immediately, capital F, which represents the probability that big Y is less than or equal to little y, is the area from minus infinity to little y under the density curve. And so probability for continuous random variables is represented by area under the density function. Here's a simple example of the density function for a continuous random variable. We talked earlier about a uniform story between 0 and 1. Here's a slight generalization of that, a uniform random variable between numbers a and b, where b is bigger than a. And it's just completely flat. And in Bayesian language, as we saw this morning, it represents a state of knowledge, a state of information that says, all I know about this quantity, capital Y, is that it lives somewhere between little a and little b. If that is the totality of your information about capital Y, you would code that information by means of probability density functions with a uniform distribution. And so since the total area has to be 1 and it's a rectangle, if the base is b minus a, then the height has to be 1 over b minus a. And so the density function is just 1 over b minus a for values that are between little a and little b, and 0 everywhere else. And the CDF for that continuous random variable, if you started accumulating up until here, if you stopped anywhere over here, you haven't got any probability yet, so you'd still be at 0. And then as soon as you start accumulating from a, since the thing is flat, you're going to accumulate at a linear rate. And so the CDF is going to go up at a linear rate until it reaches 1 at the point B. So that's what the probability density function, PDF, or just density, looks like. And this is what the CDF looks like for that same random variable. It starts out at 0. As soon as it hits A, it starts to climb linearly until it reaches 1 at the value B. And so you can work out what the equation of that line is, and it just becomes y minus A over B minus A as A ranges from A to B, and it's 0 below that and 1 above that. By far, the most famous and, quote, popular continuous random variable is the normal distribution or the Gaussian distribution. Most of the things in statistics are not named for the people who really did them first. And that's true in science as well. Most of the things in science are not named for the people who did it first. I used to teach at the University of Chicago. That was my postdoc, my first postdoc experience. And I had a colleague there named Stephen Stigler, who is by now a well-known historian of statistics. And he has seen this so pervasively that he gave it a name. He called it Stigler's law of eponymy. Eponymy is a word that has to do with what things are named for. And since he had a good sense of humor, Stigler's law of eponymy says, nothing is ever named for the person who first thought of it, comma, including Stigler's law of eponymy. And so it turns out that even though we call this the Gaussian distribution, also known as the normal distribution or the normal curve, in fact, Abraham de Moivre worked with this distribution 75 years before Gauss did and got productive results out of it. At least one of the Bernoullis knew about this distribution as well, 75 to 100 years before Gauss. And so they're working with this distribution. They just didn't choose to give it a special name. Gauss did a lot with it. And after Gauss died, people started calling it the Gaussian distribution because he did a lot with it. But that doesn't make it uniquely Gaussian. OK. And you probably remember how this works. It's the bell curve. And the bell curve is uniquely defined by two numbers, where it's centered and how spread out it is. And the center is located at the mean of the distribution. I'll say in a minute what the mean is. And the spread is governed by the standard deviation. I'll say what that is as well later on. So the mean is called mu in the random variable, and the standard deviation is called sigma. And it has this forbidding expression here. The height of the density at that point, at little y, is you go a lot of the famous symbols in math, 1 over sigma squared to 2 pi, e to the minus 1 over 2 sigma squared times y minus mu squared. So that's, and we will have to deal with that formula as we go along in our next case study next week. This distribution is continuous and has the property, of course, like they all do, that as you sweep from left to right, you're getting more and more probability. So it's a canonical one of those pictures that looks, whose CDF looks like one of those extended S-curves. Now, you remember, the CDF is the integral of the probability mass function. And so we would like to have an expression in which we worked out what that integral is in closed form, and there is no such expression. So right at the beginning of the history of probability, people bumped into the fact that they had integrals that they had to calculate that had no closed form expressions. And you may remember from your early calculus class that the thing to do at that point is to do numerical integration. You approximate the integral with a bunch of little histogram bars, like little teeny rectangles, and add them up and take the limit as the width of the rectangle goes to 0. And so numerical integration was invented around the same time as integration was. Newton already knew how to do numerical integration because he noticed that, and so did Leibniz, because they both noticed that there are lots of integrals that don't exist in closed form. So we deal with we can write the density down in closed form, but we deal with the CDF by numerical integration and then storing the numerically integrated values either in tables in the back of statistics books or in functions in packages like R. So for example, those of you who are fluent with R, the p-norm function in R, p-norm function calculates values from the cumulative distribution function. And it actually does it by what's called a rational polynomial approximation. It turns out if you take a polynomial of degree k in the numerator and a polynomial of degree k prime in the denominator, and you make k and k prime big enough and mess with the coefficients, you can get practically any shape you want. And it's surprising how closely you can approximate any shape you want, where k is just on the order of 3 or 4. K and k prime are just on the order of 3 or 4. So p-norm in R is actually calculated by taking the ratio of two polynomials. In this class, densities will typically be denoted not by f sub capital Y at little y, but by lowercase p sub capital Y evaluated at little y, p for probability density. And Even more often, people make a notational abuse, and they simply write lowercase p of lowercase y, and you're supposed to infer from the symbol little y that that's the density for the random variable capital Y. So you just don't bother to write the capital Y, and you remember by the symbol that's inside which random variable it's the density of. Similarly, we'll talk about a density for an unknown quantity theta, and a density for an unknown quantity lambda, and you know which random variable you're talking about by looking at the argument of the density function. All right, so that's random variables one at a time. Two at a time is a little more complicated. Hi. Do you need to make an announcement? Oh. Oh, and she's trying to get into the class?
Yeah.
Can one of you guys help with that?
Okay, thank you.
Thank you very much. So I'll tell the story about random variables two at a time, and then the same story works for more than two at a time as well. So now it gets notationally more cumbersome, but and there are some new ideas. The fundamental operation on two random variables at a time, let's call them capital Y1 and capital Y2, is what's called the joint cumulative distribution function of the two of them. And following the same notation, it would have to be capital F subscript capital Y1, comma, meaning and, capital Y2, evaluated the arguments lowercase y1, comma, meaning and, lowercase y2. And that's equal to just the obvious thing you do. It's the probability that big Y1 is less than or equal to little y1, and big Y2 is less than or equal to little y2. So the comma in all these expressions essentially means and. If Y1 and Y2 are both discrete, it makes sense to talk about the joint probability mass function, because then we can talk about the chance that Y1 exactly equals the value little y1 and big Y2 exactly equals the value little y2. And so we'll call that the joint probability mass function, lowercase p, and as usual, like I said before, with the slight notational abuse, we often don't write down the random variable names. And just as we did with one variable at a time, if both variables are continuous, it's natural to consider a joint density function by taking the double integral over this joint density to get back the joint CDF. So this is just like what we saw earlier, except there's two of them now. You could, of course, have a joint situation where one is discrete and one is continuous, and then one of these integrals becomes a sum. And you can talk about a probability mass function on one part of it, and you have to talk about a density on the other part. But usually, if one of them is discrete, the other one is 2, or if one of them is continuous, the other one is 2. The marginal CDFs are given by what you get by taking the joint distribution and taking the limit. If you want to know the marginal CDF for the variable y1, you take the limit of the joint CDF as the other argument goes to infinity. That makes it go away, and we get the marginal. And similarly, of course, for the other one. And the marginal density is obtained by integrating over the other dimension than the one you're interested in. So the marginal density for one of them at a time is equal to the integral of the joint density of both of them, adding up over all the other values of the other one. That is an example, a continuous example of that thing I mentioned this morning called the law of total probability. So the way you get down from high dimensions down to one dimension is you add up or integrate over all the other dimensions, the joint density function, and that gets you down to the marginal density. This is the operation is called marginalizing over the other random variable that you're getting rid of. And of course, similarly for the other one. And now that we have two of them, we can begin talking not only about how they behave jointly and how they behave marginally, but also how they behave conditionally. So we can talk about the conditional density of one of them given the other. And we just use exactly the same definition that we saw the way Mr. Bayes defined conditional probability, except we use densities in place of the probabilities that were just simply probabilities for propositions. So the conditional density of y2 given y1, evaluated at the places little y2 given little y1, is just equal to the joint density divided by the thing that you are given, that you're conditioning on. And from this it follows that if the two random variables are independent, then the joint density will be the product of the marginal densities. because you remember the general rule is that the joint would be equal to the marginal times the conditional. So it would go the chance of A and B is the chance of A times B given A. But if A and B are independent, and this is something worth taking a moment on, in Bayesian language, in the frequentist language, independence has a very narrow definition. And there is the narrow definition in the frequency story. Two random variables are independent if their joint density equals the product of their marginal densities. That's the definition of independence. And that's always seemed to me to be an unpleasantly technical definition. The Bayesian narrative for independence is much easier to talk about. Two things you're uncertain about, your uncertainty about two things that you're uncertain about is independent if information about one of them does not change the chances associated with the other one, and vice versa. So if A and B are independent, if I offer you information about B and it doesn't change the uncertainty about A, that's just how it works for independence in the Bayesian story. So that I think is intuitively a simpler narrative. Now, expected value. You were mentioning, I think, that essentially Mr. Bayes was defining probabilities through expected values. So if a real valued random variable is discrete, then its expectation, otherwise known as its mean, is just a weighted average. So you take, it's written capital E of the random variable, capital Y, and you simply take a weighted average of the values that Y takes on, weighted by the probabilities that it achieves those values. And so that means that the expected value, and the same thing happens with continuous random variables, except that sums are replaced by integrals. The expectation of a normal random variable, for example, turns out to be the mean of that random variable, the symbol I used before, mu. And if you think about what's going on, since it's a weighted average, you're taking the values and weighting them by the probabilities. The graphical interpretation of an expected value or a mean is as follows. If you made the number line out of plywood, and you made the density function out of concrete, and you put the whole thing on a sawhorse and moved it from left to right, the mean is the place where the whole thing would exactly balance and not fall either to the left or to the right. That's what's meant by taking the weighted average in that fashion there. So the mean is the balance point of a distribution. And then having defined the mean, the variance of a distribution is just defined to be the expectation of the square of how far you expect the variable to be from its middle, from its mean. So let's call that V of Y for the variance of the random variable Y. And another symbol for it is sigma squared often. And it's a measure of spread. But it's a measure of spread that is useful for some purposes and deeply counterintuitive for other purposes. And the reason that it's not so good is that the units are wrong. If Y is money in dollars, then what units does the mean come out in? No, the mean. If Y is dollars, the mean comes out in dollars, but the variance comes out in dollars squared. And who knows anything about dollars squared? So the variance was invented because it satisfies certain technical properties having to do with additive aspects we'll see later on. But you got it to get the measure of spread back on the right scale, you got to take the square root of the variance, and that's what people call the standard deviation. And you remember about the normal curve that it has the property, you can look it up in tables. If you start at the mean and go one standard deviation either way, you find about 68% of the probabilities in there. And so basically, if you were looking at something that was normally distributed, you expect it to be within one standard deviation of its mean around 2/3 of the time. And that can be used to construct an approximate graphical estimate of the standard deviation. If I showed you a normal curve and I ask you to guess at the standard deviation, you can try on various values, pick whatever mu is obvious in the picture, and try on various values of sigma until it looks like it's wide enough to get about 2/3 of the area, and that'll give you a graphical approximation to the standard deviation. Okay, that's about all we need in the way of stuff like that. And now we can go back to the narrative in the organized notes. So let's do so. Here I want to go back to this. And I'm now going to try to show it also on the other screen, if I could get the attention of this machine. What do you have to do to an Apple machine to get its attention? Pardon? Oh, I have it there, not very much here for some reason. Okay, now it's coming back in. Okay, so I'm going to try to give you guys both screens by running both laptops. That's the only way that we could kludgely find to get both screens to run the way they are supposed to. So this is a unit in the course called exchangeability and conjugate modeling. Unless you've already done Bayesian stuff, you don't know what either of those words mean, but pretty soon you will. So the first unit here, in the first subunit of this story, we're going to talk about probability as a method of quantifying your uncertainty about things you can actually observe. And I'm going to focus on a case study that involves binary outcomes. I do a lot of my applied work with people in the division of research of the Kaiser Permanente hospital chain in Northern California. We are often trying to measure the quality of care that a hospital delivers to its patients. And one of the important aspects of quality of care is looking at the outcomes of that care. So for instance, at a very gross and naive level, you can look at the mortality rate for a disease like heart attack and compare it across various hospitals. And your very first naive impression might be that hospitals that have a higher mortality rate for heart attack are maybe having lower quality of care because more of their patients are dying. And in the very early stages of trying to make comparisons among hospitals, people actually proposed that as a way of deciding which were the good and the bad hospitals. And approximately 1.5 seconds after people proposed that, everybody noticed that that was stupid, right? Because some hospitals treat sicker patients than other hospitals. The Mayo Clinic, for example, and the Cleveland Clinic are places that specialize in working with very hard to solve medical cases. So the raw mortality rate at those places is obviously going to be much higher than the mortality rate at some sleepy rural hospital where not much is going on, right? But outcomes are definitely a part of the story. And in this case study, we're going to talk about outcomes, and we're going to talk about a binary outcome, whether a patient dies or not. One thing that turns out in quality of care studies is that given the current state of understanding in medicine at any moment in time, and you could have said this 200 years ago, and we'll still be saying it 200 years from now, there are some conditions that current medical understanding pretty much can't do anything about, and other conditions where we have a lot of leverage over them. And diseases where good treatment of the patient leads to good outcomes are diseases that are valuable to look at for the purpose of quality of care. What is done for patients on behalf of them to get to the outcomes is called process in the world of quality of care. And so you can measure the quality of hospital processes, and you can measure the quality of hospital outcomes, and you can try to find a disease in which the so-called process outcome link is strong. If you were looking at mortality as an outcome and you studied end-stage cancer or end-stage renal disease, end-stage meaning the person's about to die and we don't know anything about how to fix them, then that's a stupid way to look for quality of care, right? Because all those patients are going to die really soon, and you can't tell who's giving better care than another unless you look at things like the quality of the palliative measures you give for pain and things of that kind. But if you pick a disease like heart attack, it turns out in America as well as everywhere else in the world, good processes of care lead to good outcomes with heart attack, and bad processes lead to bad outcomes. And I will tell you from the RAND quality of care study that I worked on, I mentioned before, that the disparity between good and bad is actually much wider than you would think in America. If you have a heart attack at a really good hospital and you compare your risk of dying within 30 days of admission to having a heart attack at a really poor hospital in terms of quality of care, the ratio of those probabilities of dying is more than 3 in America. Your chance of dying is triple in a bad hospital over a good one. My advice to you, if you're going to have a heart attack, is to have it on the sidewalk out in front of a major teaching hospital. Find yourself a big city like New York and get an apartment which is right next door to one of the major teaching hospitals in New York. And if you have your heart attack, you have a much better chance of surviving it. A little sleepy rural hospital where they haven't paid much attention to what good care is, even by reading the medical journals, your chance of dying from the heart attack can be 3 times higher than it would be if you went to the best places. So here we're going to look at outcomes only because it's too complicated to start talking about the process outcome link. Later on, we may have time to talk about that. But so I'm going to...
When the ambulances come and pick up people here at Google,
Yep.
and they think it's hard, they take them to Stanford, even the El Camino or so.
There you go. And by the way, what they're doing probably in the ambulance is they're probably giving them a variety of so-called clot-busting drugs to keep any of the blood clots that develop as a part of the heart attack from getting to the brain. Because one of the things that can happen to you is you can stroke out after a heart attack. And so they have all these drugs now that they give to people right while they're lying on the ground with a heart attack and right while they're in the ambulance on the way to the. Yeah, no, I really believe that. Okay, so we're going to talk about heart attack, and the doctors all call that acute myocardial infarction, to be fancy, AMI for short. And I have one particular hospital in Santa Cruz I'm thinking about. It's not part of the Kaiser chain. It's just the one major hospital in Santa Cruz. It's called the Dominican Hospital, DH for short. And if this were your problem, you'd be thinking about a different hospital, of course. And I decide at a gross level of looking at quality of care to examine the medical records of all patients treated at the Dominican Hospital in one particular time window, let's say from the beginning of 2006 to the end of 2009. So that's a 4-year-long window. And I just keep track of the mortality outcome and look and see what's going on. In that time window, it turns out that there'll be about 400 patients, heart attack patients at the Dominican Hospital. And so little n, what's going to be my sample size, we'll call it, is 400 here. It's some number, it's some integer, not exactly round 400, but I'll just use 400 as a round number. And so to keep things simple, I'm going to ignore process for the moment and focus just on that one outcome. Death status or mortality, yes, for being dead 30 days, within 30 days of admission, and 0 otherwise. If you focus on mortality without saying how long the time window is, then obviously everybody dies, right? So you have to pick a time window, and it needs to be relatively short in relation to when they were admitted. Otherwise, they might die by being hit by a bus or something like that. So, and yet in-hospital mortality turns out not to be a good thing to use because some hospitals keep their patients longer than other hospitals. And obviously, if you keep your patient longer, that's a longer window in which you have a chance to die. But on the other hand, it's also maybe better care for you for keeping you longer. So it's confusing. So what people do is they pick a standard window like 30 days from admission, and you look at the 30-day death rate. Okay. Now, of course, this is going to depend not only on process, it's going to depend not only also on sickness at admission, it will also actually depend on what are called structural things. You were talking about Stanford, whether the hospital you're at does or does not have the very greatest, most recent imaging machine, for example, for really finding out what's going on inside people. That's an example of structural differences from one hospital to another. I'm going to ignore all that stuff and just focus on the outcomes. So I'm about to see a vector of 1s and 0s that's of length 400. I haven't seen any of that data yet. What can I say about that beforehand? I'm uncertain about that vector. I'm uncertain about all sorts of aspects about it. So I have uncertainty. Can I use the language of probability? Let's call those outcomes capital Y1 through capital Yn. They're all binary. And so can I use probability to quantify my uncertainty about it? And we agreed yes in the first case study, and we'll see it's yes again here. And the classical approach is already not that fun to try to use because it's too simplistic. So I'm going to review the frequentist approach to this problem and show you the Bayesian approach. First, let me remind you of the frequentist story. Remember the frequentist definition of probability. In that definition, you have to tell a story in which something is being repeated over and over again. And so you've got these 400 people. Were they, for instance, the result of a random sampling process? Did I pick these 400 patients at random from all of the heart attack patients at the Dominican Hospital in that 4-year time window? Well, no, I didn't. I took all the Dominican Hospital heart attack patients in that window. But if they had been a random sample, then the standard frequentist dodge is to start thinking about what you would have gotten if you'd taken other random samples from the same population, namely the broader universe you're trying to generalize to. If all I wanted to do was to observe those 400 1s and 0s and tell you how things came out, that would just be description using the language I used this morning. But if I want to draw inference about the underlying process that gave rise to that stream of 1s and 0s, that involves generalizing outward from those 400 1s and 0s to a bigger universe. And in the usual statistician's language, that involves thinking of the data as either literally a sample from a larger universe called the population, or like a random sample from that population. And if you can tell that story, then the frequentist machinery is up and running for you, because you can think about what would have happened if you had gotten a different random sample also of size 400. That's the way the frequentist story works. So if you can tell that story, then the randomness in your probability statements refers to the process of what you might get if you were to repeat the sampling over and over. And in that way, the y sub i's become random variables whose probability distribution is determined by the hypothetical repeated sampling. So let me draw a little diagram that expresses exactly what's going on in the world of frequentist modeling of this kind. In this diagram, there's going to be 3 parts to it. There's going to be a part called the population viewed as a data set. And I need to switch over to this camera here. There's going to be a place called a data set called the population. There's going to be a smaller data set called the sample. And there's going to be a third data set called the repeated sampling data set. And it's going to be the biggest one yet. And in my diagram, I'm going to draw an arrow from the population to the sample, like in that balloon diagram I showed before, going from the population to the sample. And it's always easy to start with the sample. And so the sample always consists of the observed, whatever the observed things are that you observed. And here it's the observed patients. And you can right away talk about the sample size, as people call it, the number of rows in the sample data set, which here is 400. And you can think about the composition of the data set, and it's going to consist of ones and zeros, where I make a little note in the margin for myself, where 1 equals died and 0 equals not. Okay, so that pretty well completely defines the sample. And I could begin thinking about populations, rather sample summaries. For example, it might be pretty hard to predict the exact pattern of ones and zeros, but it might not be all that hard to keep track of the average of the ones and zeros, which would be the mortality rate in this particular sample. And so the way you get a rate from a 1, 0 variable is you take its mean. And because the thing we're going to be using the data for as an estimate of over in the population is a proportion or a probability, people often refer to this with a name like p hat. I forget it looks like in the notes that I've got on the board, on the PDF there, I call it theta hat, so let's use that. Hat is often used in the frequentist world to mean an estimate of something, where an estimate means a number in the sample that's a good guess for the thing that's analogous to it back in the population. Okay, so that completely describes the sample. It's going to turn out in this sample that p hat comes out, I think, 0.18. So the mortality rate, the observed mortality rate, was about 18%. If that sounds high to you, that number in a rural hospital could easily have been 35%. Now comes the tough part in the frequentist narrative, and it's also going to be a tough part in the Bayesian narrative with observational data of this kind. Given that the data consists of an observational data set, just the 400 people who happen to show up at the Dominican hospital with an admission diagnosis of heart attack in that 4-year time window, I can't argue that those 400 people are literally a random sample of anything. They're just the people who showed up. So I want to try to argue somehow that this data set is like a sample taken at random. And in fact, I'd like to try to tell you a story in which it's like an independent, identically distributed sample, because that makes the math easier. Remember, the independent, identically distributed idea says the independent part means that what you get on the first random variable doesn't influence what you get on the second one, and so on. They're independent of each other. And the identically distributed part means they all follow the same probability behavior. And a way to do that is to use various methods of random sampling. If I pick people out, if I pick one person at random and put that person in the sample, and then the simplest way is I put that person back in the population and then take out one more person at random and put that second person in the sample, and I keep doing that. That's an example of an independent, identically distributed sample. Well, see, that's the exact point here. I have to try to tell a story of this kind for the frequentist inferential machinery to work at all. And his point is a really good one. Whenever we try to use statistics to infer outward from our data set, the most important scientific question is to address the issue, what is the broadest scope of valid generalizability outward from the data I have? And that defines the population that you're trying to reason toward with the inferential machinery. And your point is well taken. If we were trying to set up the population as all heart attack patients in California, for example, during that period of time, and if the people who were in the catchment basin of the Dominican hospital were systematically different from everybody else in California, then this would turn out to be a really bad story, really bad modeling story. But let's do it the other way around. Let's think about the people we have and see if we can tell a narrative in which we can identify a population that they are like a random sample from. See if we can do that. Actually, I'm going to postpone that for a minute to continue telling you about the way the diagram works. If we can identify such a population, and I'll try to write some words in up here that will describe that, then that population will generally be a finite set of patients. So let's use the population size. Let's call capital N the population size. I don't know what it is, but I'm going to hope that it's a lot bigger than little n, because I really do want to generalize outward from these 400 people to a bigger universe. And this data set here is also going to consist of ones and zeros. Which variable am I working with? I should have said the variable in question in the sample is a variable died question mark, and of course it's the same variable over here in the population. Now, if you could round up everybody in the population, and I haven't said who that is yet, but if you could round them all up and add up their ones and zeros and divide by how many there are, you would get a thing that we could agree to call the population mean. And it would not necessarily be that number p hat, right? Because p hat's just what we got in the sample. Nor would it be theta hat, which is another name for the same thing. It would be some other number. I'm going to call it theta. You could think of it also as lowercase p. And its logical status is I don't know what it is. I do know what's going on over here in the sample, but I don't know what's going on in the population, so I'm going to put a question mark next to it. That pretty well completely defines the population part of the diagram as well, except for this crucial story here. I have to be able to say, who are these people that I'm trying to generalize to? If I can't say who they are, then the inferential exercise is pretty close to meaningless. And yet, if I put this data into an R function that analyzes data like this and press the button, it will give me inferential answers. It's just that those inferential answers may not have any meaning because I haven't been able to say what exactly is the population that I'm trying to generalize to. Theta is the mean of some patients, but I haven't said which patients yet. Now, Fisher, I keep mentioning his name. He was a towering figure in frequentist statistics in the 20th century. He was also a very, very good geneticist as well. He had an automatic and glib answer to this question. Here was Fisher's answer. The population is the hypothetical universe of all the sampling units you could have gotten if you went and repeated the experiment. That's his answer. He didn't care about filling in that question mark. He was interested in the math of if you could fill in that question mark, how should you now draw reasonable conclusions about theta on the basis of the data in the sample? So Fisher, as great as he was as a scientist, was really disappointing on this score. He punted on this question. Now let's see. Let me skip over for a moment because I'm going to forget about this thing at the bottom here, which talks about Bernoulli, blah, blah. We'll come back to that in a minute. But let's now face this issue. So what is the population exactly that I'm going to try to generalize to? Well, as I mentioned, Fisher's naive and glib story is all heart attack patients who might have come to the Dominican hospital in that 4-year period if the world had turned out differently in some way, if some butterfly in Brazil had flapped its wings differently or whatever. That's obviously a ridiculous answer. Now, another thing we could try, people generally, when they have a data set that is located at a particular point in time and space, they try often in generalizing from it, they try to generalize either in time or in space. So let's try generalizing in time. Suppose I open up a 10-year time window in which 2006 to 2009 is inside that interval, and I try to say that the population of interest is all heart attack patients at this one hospital from the years from 2000 to 2015, for example. That is a possible population, and this is indeed a sample from that population, right? Because I defined the population in such a way that it's a sample from it. Is it a random sample from that population? Well, no. It's what people call a cluster sample temporally, in which all the data came in that one 4-year window and none of the data came before or after. In order for this to be like a random sample from that population, I would have to make a strong assumption which is untestable on the basis of the data. I would have to make an assumption about time homogeneity, the process. And there's no way to test that assumption internal to my data set. If there were no time trend in my data set, that wouldn't force it to be true that there wasn't any time trend outside that interval. If there was a time trend in my data set, that wouldn't force it automatically that the same time trend was going on before and after. So that's one way to create a population here, but it rests on a completely untestable assumption. Now, what about generalizing outward in space instead? Suppose I focus on that same time window, but now I try to say that I'm going to think of this as like a random sample from all heart attack patients in all of California, for instance, in that 4-year time window. And of course, that's a problem for the same reason that that gentleman said over there. I don't have a random sample from all patients in California. I have another, again, one of these things called a cluster sample, consisting of all the patients from one hospital and none of the patients from any other hospitals. And among other things, you can imagine that that's going to be a problem for the following reason. Quality of care turns out to be a hospital-specific phenomenon. The doctors, there's a kind of culture inside each hospital because there are chief doctors at each hospital, and they get all the other doctors together, and they all talk about how to treat patients. And so there's a kind of homogeneity of care for heart attack inside each hospital that differs from the homogeneity of care in other hospitals. And so think about it. On the one hand, I offer you a deterministic sample of all 400 of the heart attack patients inside the Dominican hospital. And on the other hand, I offer you a random sample of 400 patients from the whole state. How are those two samples going to differ from each other? Will the sample from the Dominican hospital reflect all of the variation that you would see across the whole state? Certainly not. In fact, because the patients are treated in a way that's internally homogeneous, there will be less variability in the ones and zeros inside that hospital than there would be of 400 people across the whole state. That's called intra-cluster correlation. There's a name for that. People in sampling theory think about this stuff all the time. That's called a positive intra-cluster correlation. It says that patients in a given hospital tend to be more similar to each other than would a random sample be of the same size. And so basically, every way we think of trying to generalize outward from this observational sample, we're in some trouble. I suppose you could try to tell a narrative of the form, sometimes the ambulances take the patients to Dominican and sometimes they take them somewhere else. And it's based upon how close you are to Dominican or not. And that creates a kind of catchment basin, as I said before, for Dominican. And right at the edge of that catchment basin, there might be some coin tossing, so to speak, and the ambulance might have gone one way or might have gone the other way. My point is that we actually have a hard time defining what the population is that it's appropriate to generalize outward to with this data set. And that's true in all observational settings. And this lesson applies with equal force to those of you here in the tech industry. You've got a data set. You're perfectly capable of, and more power to you, you're perfectly capable of describing the data that you've got. But if you want to use statistical methods to do inference on that data set, you have to be prepared to say, what is the population that you're able to legitimately generalize outward to? And oftentimes here in the Valley, the population you're interested in is the future. What would happen at the same people coming to Google or people coming to eBay or people coming to Yahoo in the future if the web experience were like this versus like this, for example. And you have to be able to convince yourself to infer to those future people, you have to be able to convince yourself that what happened now is like what you would have gotten if you had been able to sample the future. And if you can't convince yourself of that, then don't do inference because the numbers, I mean, your computer will do it for you, right? There's buttons inside R for doing statistical tests and confidence intervals and all that stuff, and buttons inside all the other routines and so on. And you press the button and no bolt of lightning comes down from the sky and fries you. But the numbers that come out may not mean anything because you haven't said yet what the population is that you're trying to generalize to, and you haven't convinced yourself and others that your sample is like a random sample from that population. So there's a really important thing that everybody has to think about all the time, and that isn't talked about as much as it should be in the statistical world, particularly in the textbooks and so on. For the sake of understanding how we could draw inferences, if we had been able to define a population, I want to go ahead and do so, but I see it's time again, I think, for our next break, isn't it? It's 2:30, yes. So let's take our next break, and I'll start again at 2:45.